Okay, so stereoisomerism. We've talked a little bit about some basic forms of isomerism, and this is what we're looking at covering by the end of it. So we've focused already on structural isomerism, and we need to talk more about stereoisomerism. There, you can have a read of that. The stereoisomerism is divided into two classes, and most of this session, in fact, nearly all of it, is going to be about this form of it here, and it's because we can talk about cis-trans, E and Z forms, and optical isomerism as well. This is just going to be a tiny little bit that we need to mention. Alright, so this is what we need to be able to do as well as all the other knowledge that you saw on the last page. So breaking that chart down a little bit, you can see the stuff here that we've covered. So positional isomers, hydrocarbon chain isomers, and functional group isomers. If we wanted to recap those a little bit, maybe over here we could have this being one form. There's our hydroxyl group there. If we move that functional group to a different place, different position, it'd be something like that. Hydrocarbon chain isomers, well, examples that we looked at there, if we had formula C4H10, then we could draw that out as a straight chain, or an isomer of that would also be with a branch like that. Right. And the last one, functional group isomers, the example of that we've maybe saw was the relationship between an ester as one form and a carboxylic acid as another. So if we have this as our group in, I don't know, whatever it is, propanoic acid, we could also take those atoms and make some sort of ester combination from that. Right, so this is what we're doing today. Stereoisomers, different spatial arrangements of atoms and molecules. As I said, there's two forms. Conformational, which is kind of short-lived stuff. It involves rotation about a sigma bond. And configurational, where we would need to break and remake covalent bonds to end up with the alternative isomer. That's taken from the course guide again. Alright, let's do conformational and get that out of the way. So if we think of, this could be ethane, sorry, this is ethane. Now we know that there's free rotation around a carbon-carbon double bond, sorry, free rotation around a carbon-carbon single bond there, which you can see. So we can spin this end around. Now this form, this staggered form, is going to be very slightly more stable than this form, because if we think of these groups up here, there's going to be a little bit of maybe steric hindrance there, with these groups being in close proximity. Now it would be obviously much more marked if these, instead of being H's, were methyl groups, because methyl groups are that much bigger. It really would be a tight squeeze to get them that close together there. So this form is maybe more favoured, the staggered form. And if you think of work you've done with model building kits, probably this is more the shapes that you've been producing, rather than things like that where we end up with these bits and pieces getting in the way of each other. So that's conformational isomerism. Now we're on to the configurational stuff. And there's two aspects to this that we have to look at. Firstly would be optical isomers. So what we start off with is a chiral or asymmetric carbon, and that's something that's got 4 different groups attached. Now we use these hashes and wedges to show us 3 dimensions. So this means it's going into the page, and this wedge means it's coming out of the page. This is in the plane of the page, so it's this tetrahedral arrangement. And if we drop our mirror plane down here, and if we have our lines going in, that's got the iodine on the end, the wedge coming out has got a methyl group, and the dash is going into the page has got the OH group, we end up with these mirror images, right? And these are non-superimposable, and we refer to them as a pair of enantiomers. Now enantiomers have an unusual property in that they can rotate the plane of polarized light. So if you shine polarized light, and we'll talk about what that is in a minute, it means it's light that's just moving in one plane. So this is like this. The light comes in, this would actually rotate it. One will rotate it one way, the other one will rotate it by the same amount the other way. And if I have equal concentrations of these two enantiomers, my substance isn't able to rotate that light because, if you like, they kind of cancel each other out. And we describe that mixture as a racemic mixture. Now these structures, whilst talking about this polarized light, they're also relevant for things like biochemistry. Think of enzymes, very specific active sites that substances have to fit in. And so this three-dimensional arrangement is very, very important for whether the substrate can fit into that active site. So this is our polar emitter. This is us generating light that is just moving in one plane. So here I've got many, many different planes of light, right, all different angles with respect to each other. Here I've got just one coming through, and that sample will bend it, will rotate it one way or another, depending on which of those enantiomers it is, and we can detect that as well. Right, so this diagram here talks again about enantiomers. You can see that these are mirror images. But if we've got two chiral centers, so there's one here, that's got 4 different groups attached. That also has 4 different groups attached. So I've got 2 chiral centers. I end up with a situation where I've possibly got diastereomers. So whilst I can get my pairs of enantiomers as before, 2 of those will be diastereomers, right? They're not going to be mirror images. So just bear that in mind. If you've got 2 chiral centers, you can end up with this extra situation where you've got diastereomers. Right, this used to be referred to as geometric isomerism, but we're not to use that name anymore apparently. So if I have a situation where I've got a double bond or I've got a ring like this, both of these situations give me locked configurations, right? We saw with the conformational stuff that we could rotate around that sigma bond. We can't rotate around a double bond because, if you remember, we've got overlapping pi orbitals, p orbitals forming pi bonds above and below the plane. So I can't rotate around this, so this is locked. So I need to find a system whereby I can explain that this, where these are on the same side, is different to this, where they are on the opposite sides. Likewise, if it's a ring, cyclo compound, so this would be cyclobutane, it's locked. I can't unplug the ring and then rejoin it back up. So these will always be on opposite sides, and these will always be on the same side, right? And we can look at the same example in some inorganic compounds as well. Again, these aren't going to be able to twist around and be in different places. It's locked in this position. And if we've got just 2 different substituents, as we have here, methyl groups and H's, or black balls and nothings, we can use this terminology cis and trans. Trans, opposite to each other, transatlantic. Cis means that they're on the same side as each other. So that's where we get these prefixes explaining which is which. Now that can give us slight differences in physical properties. So depending on how things pack together, we might find that the van der Waals forces, the London dispersion forces are slightly stronger, in which case we have a slightly higher melting point. And in rare occasions, we might find that 2 groups, because of the structure of the molecule, have ended up in close proximity, and they can actually react with each other, and we end up with a whole new compound. Whereas if they're trans, like this, it's not going to happen for us. Right, now if we have more than 2 constituents, then we have to use this system, E and Z. E for entgegen, Z for zusammen. 2 good German words. Z meaning together, E meaning opposite. And to decide kind of what are we going to call as the most important when we're deciding whether they're opposite or together, we use a system called the Kernigel-Prelog rules. And in its simplest terms, you choose the one that has the highest atomic number and give that the highest priority. So if we look from this carbon and we move out atom by atom, then that's going to be our number 1. Highest priority is O. and I've got a choice between these C's. So they're going to be equal. So the next move on to the next atom. That's it, that one there, which beats the H. So that's my second highest priority, third, fourth. And we can do that with side chains around double bonds as well. So if I look here, I've got the possibility of geometric isomers. And so I've got CH3 there, CH2, CH3. This is my number one priority on this side. Between these two, this is my number one priority there. CH3 beats H, if you like. Likewise down here, this is going to be higher priority than that. This is going to be higher priority than that. So that one is the E form. Right, so that's what we've covered so far. You can check through that as well. And that's the sources.